4.8 Compressor and Pumps. Compressors and pumps are devices that increase pressure of fluids. Their function is the same, to increase the pressure of a fluid. So compressor is used to increase the pressure of a gas, and pump is used to increase the pressure of a liquid. So fluid enters the device at low pressure, and work is supplied to rotate the shaft in the compressors and pumps. They require work input. So compressors and pumps are work-consuming devices. On the contrary, turbines are work-producing devices. As fluid passes through the device, the blades compress the fluid. So the fluid leaves the device at high pressure. The energy balance in general form is shown here. If the change in kinetic energy of flowing matter is negligible, kinetic energy drops out. If the change in potential energy of flowing matter is negligible, potential energy drops out. If the compressors or pumps are well insulated, there is no heat transfer with the surrounding. So Q dot drops out. And since the compressors and pumps are work-consuming devices, W should be negative. Example 4.5. Air enters a compressor operating at steady state at a pressure of 1 bar and a temperature of 290 Kelvin and a velocity of 6 meters per second through an inlet with an area of 0.1 meters squared. So the pressure, temperature, velocity, and area at the inlet are given. So we can fix the state at the inlet. So at the exit, pressure, temperature, velocities are given. So we can fix the state at the exit. Heat transfer from the compressor to its surroundings occur at a rate of 180 kJ per minute. So in these questions, the compressor is not well insulated, so there is a heat loss to the surrounding. Employing the ideal gas model, calculate the power input to the compressor in kilowatt. So air is the working fluid, and we assume air is an ideal gas. It satisfied ideal gas law. We are going to apply the energy balance equations for open systems. And we are going to assume that the potential energy difference between the inlet and outlet is negligible. And we want to determine how much work is required to compress the air at the given conditions. So we solve it for work. So we know the heat loss to the surroundings. We fix the state at the inlet and outlet, so we can determine enthalpy at the inlet and outlet. The velocity at the inlet and outlets are given. The only thing is unknown here is m dot, mass flow rate. Mass flow rate can be determined by volumetric flow rate divided by the specific volume at the inlet. Since air is considered an ideal gas, we use ideal gas law to determine the specific volume. Heat loss to the surrounding is kilojoule per minute, and we are going to convert it to kilojoule per second. So multiply by, and enthalpy at state 1, 290 Kelvin. This is H1. Recall that enthalpy is only function of temperature for ideal gases. Enthalpy at state 2 at 450 Kelvin. Enthalpy is here. Since compressor is a work-consuming device, W is negative. If W is positive for compressor, then something wrong with your calculation. So check your calculation again.